Swayam Prabha. Digital India. Educated India.
Okay, so let's continue our discussion related to Introduction to Electronics. This is lecture number 11. And in the last lecture, we were discussing analysis of circuits containing capacitor or an inductor. And today we continue with that particular discussion. And in particular, in the last lecture, we were looking at circuits containing only one single capacitance and one single inductor. And today we'll be spending most of our time looking at circuits containing both capacitors and inductors. So these are, we will see that these circuits belong to second order systems because the differential equation that we get has a second derivative in it compared to a single capacitance and a single inductor circuit, which were first order circuits, first order systems described by first order differential equation. And quickly, a little bit of background. So while we analyze these circuits, we need to remember that voltage across the capacitor cannot change instantaneously because that would then require infinite current. So that's something that we remember while analyzing. The other thing is, similarly, the current across an inductor cannot change instantaneously. And because that would require a very high or an infinite voltage, so that's also not possible in practical cases. So the current also does not change instantaneously, and the voltage across a capacitor does not change instantaneously. So these are two things that we will keep at the back of our mind when we try and analyze the circuits here. So in the last lecture, we saw a circuit consisting of a single capacitor and a resistor, and we saw that it is described by a first order differential equation. If we were to write a equation describing the capacitor voltage, so X would be capacitor voltage here, it would be described by a first order differential equation consisting of the first derivative of capacitor voltage as a function of time. And this general solution is of the form of X could be voltage or current, could be X infinity, the steady state value, the initial value minus the steady state value, and e to the power minus a1t. And a1 is the time constant associated with the circuit. So when we look at this particular circuit, is described by this capacitor voltage related to the supply voltage Vs, 1 minus e to the power minus t by Rc. Rc is the time constant of the circuit here. And this is how the capacitor charges up, and we saw that in one time constant it reaches 0.63% of its final value. You need to wait for at least 3 time constants to reach close to 95% of its final value. And if you want to within 1% of the final value, you'll have to wait for at least 5 time constants. So this was something that we discussed in the last lecture here. Now we also discussed the circuits containing of one single inductor. So let's look at a very quick application of this particular circuit before we go on to circuits containing of resistors, inductors, and capacitors, both of them. So let's say we have a circuit like this RL circuit, and we close the switch. And if we close the switch, we had looked at it, the current across the inductor will be initially 0 and will gradually build up to its final value. So under steady state, we know the inductor will be a short, so the final current is going to be Vs by R, but the inductor will take time and will slowly rise to its final value, will be described by Vs by R 1 minus e to the power minus t by tau here. So this shows the buildup of inductor current. And the time constant is, note that t will be equal to L divided by R here. So now we can do something interesting with this particular circuit. Suppose we, after the switch is closed for a long time, so the current through the inductor is Vs by R, we suddenly open the switch. Let's say, let's say the values are such that L and R, the time constant is very small, let's say in microseconds or so. So after 0.5 millisecond, a steady state is there in the circuit. And after 0.5 millisecond, let's say we open the switch. The 0.5 millisecond is arbitrary, so don't worry too much about it. So we open the switch. Now, if we open the switch, we know that the current through the inductor cannot change instantaneously, so it has to find a path for the current to continue to flow. The current is flowing in this direction here. okay, from top to bottom here. And the value is, if we have R1 here, the value will be Vs by R1 here. So the current continues to flow. But if we suddenly open the switch, well, we need to provide a path for this current to flow. Otherwise, there will be arcing and other things happening at the switch here. So let's, so the current is, let's say R1 is, we'll see as an example, let's say 10 volt, and R1 is, let's say 100 ohms. So maybe 100 milliamperes is flowing till this particular point of time. So when we suddenly open the switch, let's add a resistor R2. So the current will continue to flow through R2, right? The current will continue to flow through R2. Now R2 provides a path for current to continue to flow. And the current would, of course, then we can write down the equation. The current would then decay in the manner that is shown over here, right? So the current would exponentially decay to a final value, because now there is no source here. So final value, steady state value is 0. But it starts from a value of 100 milliamperes, let's say, depending on the values of the resistors. Okay, so it will decrease, Vs by R1 is this initial value, exponent minus t by tau here. Okay, so the current continues to flow like this here. All right. Now, this is where things become interesting. If we choose a value of R2, let's say, which is large, let's say considerably larger than R1. So if this is 100 ohms, we have chosen a value which is 50 times higher, R2 here. So note that this current the current of 100 milliamperes starts with 100 milliamperes, so it continues to flow. And now the path is like this here. So note that the current is flowing in the in this particular direction here. And the voltage here is then current multiplied by 5 kilo ohms. The initial current is 100 milliamperes multiplied by 5 kilo ohms, so minus 500 volt. And then, of course, as the current decays, the voltage across R2 also decays, and it comes back to its final value, which is 0. So what we have shown here is an interesting application of an inductor, that if you close the switch and allow the inductor current to reach a steady state, and then suddenly open the switch and now put a large resistor in the path of the current, because the current has to be continuous, so that current, which was 100 milliamperes here, will flow through this large resistor also, and thereby generate a large voltage here. And this principle, so one is able to generate from 10 volt a voltage, at least momentarily for some time, one is able to generate a voltage which is minus 500 volts here, right? So by this means, through use of an inductor and a resistor, we can generate very, very high voltages here. And a principle like this is for example, used in tube lights, for example. Tube lights would require a higher voltage momentarily to cause a discharge in the gas here. And a principle like this is, we have choke, which is an inductor here. And a principle like this is used to generate a high voltage to cause a breakdown in the gas and result in current flow. All right, so a very simple application of an RL circuit for generating very high voltages momentarily here. And of course, you can control the time constants by choosing the value of the inductor here. And if you choose the value of the inductor to be large, then L by R is large, and the current can flow for a longer period of time. Okay. All right. Second order system. So an R and a C, if you have one single resistor and one single capacitor, we said is described by a single derivative in the equation, and it's a first order differential equation, and we call it a first order system. And we had seen in the last lecture that if I add another R and a C, and we have all the equations that are over here, simple equations, and if we manipulate it and finally write down, let's say, what does the capacitor voltage across C2 look like, we get this equation here. And we see that the equation is a second order differential equation with a second derivative being present here. And in this case, we can show that the output voltage will have two time constants, e to the power s1t and e to the power s2t here. So two time constants will be there, unlike a single RC circuit or an RL circuit, which was characterized by single time constant. So now things become more complicated. Let me show you an example here. So we have an RC circuit here, two resistors and two capacitors, both of them are the same. And we are looking at, let's say, the charging of this particular capacitor here. And at first glance, it seems that the charging is just like we are charging a normal single RC circuit here. But if you examine especially close to this particular part, which is shown here, you can see the charging is sort of odd here. Because normally the charging is, if you call this as a convex kind of a curve, then here there is, you can see some kind of a concave here, and initially this voltage is not charging at all, and then the charge across the capacitor starts building up, which we can understand because the charging of C2 depends on the charge on charging of C1. So first the C1 has to get charged a little bit through this R1, then only once the voltage here builds up, this voltage here would then charge up C2. So the charging of C2 is delayed a bit here. So you can see that here, and you can see it even more if you put a third order system with 3 capacitors here, RC here, and an RC here. If we were to write down a differential equation, it would have a third derivative also. And it would be characterized in general by 3 time constants. There would be 3 exponentials with 3 different time constants. And we can see the behavior here is not a simple exponential, naturally, because we have 3 different exponentials there. And you can see we are looking at this final voltage here, and you can see even more of this delay part here. So for a while V4 is not changing at all, and then it starts charging. And it's sort of understandable that this capacitor has to charge, and then this has to charge before then, you know, enough voltage builds up to cause a charging of C3. So this bit of delay that is there here. So the point is, as you add more capacitors and more resistors in the circuit, and as the system progresses from first to second and third order and so on, the charging, it is still charging. We know a capacitor has to charge to its final value, so that is okay. But the charging becomes more complicated, characterized by several time constants. And so what we'll do is, in the remaining period, we'll look at a special case of a second order system, which we call as a RLC circuit. So we have a resistance, we have an inductance, and we have a capacitance. And we'll see that is characterized by second order differential equation. So that's why we are calling it a second order system. We are calling it series RLC circuit because all the elements RLC are connected in series. The same current is flowing through R, L, and C here. So what we want to see is initially is that if we, let's say we initially close the switch at time t equal to 0. Before that, let's say the circuit is open, there is no current in the inductor, there is no voltage across the capacitor. So the capacitor is uncharged. So basically the circuit is in unperturbed state, with zero currents and voltages. And at t equal to 0, we close it, right? So we need to mathematically, let's look at it first, how we describe it. So we have this equation. If I write KVL, Vs equal to the current flowing here, I times R, that's the drop here. Then the drop across an inductor is L di by dt, and the drop across the capacitor is, let's say, Vc. And we would like to obtain a equation in terms of the voltage across the capacitor. We want to know what is the voltage across the capacitor as a function of time. Note that once you obtain a voltage across the capacitor as a function of time, you can take the derivative and calculate what is the current flowing here, because the current is nothing but C dVc by dt here. So we'll know the current here, and therefore you know the current in the circuit here. If you multiply current by R, you know the voltage drop here, you know the voltage drop anyway here. You can find out VL also either through L di by dt or through Kirchhoff's voltage law. So once you obtain Vc as a function of time, you know everything else in the circuit here. And so we write I equal to C dV by dt, that's the current flowing here. And we substitute this I equal to C dV by dt in this particular equation here. So we get this one here. So we can already see a first derivative here, a second derivative here, and then a simple term in terms of Vc, and that's the applied voltage here. We can rewrite this particular expression in this particular form here. So we take basically, second derivative is put here, d square Vc by dt square RL dVc by dt plus Vc by LC equal to Vs by LC. So you have a second order differential equation, and that's why we call it a second order system. And there are 2 parts to the solution of a differential equation. One is the force part and one is the natural part. So the force part is because of this Vs, and that is very simple. We'll come to that later on. So let's look at the natural response of the second order system. So we'll put this, let's say for the moment, Vs by LC is 0 here. And if we can easily, will not go into the mathematics of it, we can show that the solution to this particular equation is of the form, in general, is A e to the power st here. So if we take a e to the power st, substitute it here. So do a derivative, second derivative here, first derivative here, and if you substitute it here, you'll get this equation here. A s square e to the power st r by l, and so on and so forth. E to the power st is, we can take it out, and so we get this equation here. S square r by l s plus 1 over LC. So what is this s? S is a time constant here, right? Time constant in this exponential here. And because it's a second order, it's a quadratic equation, we'll get two values of s. So we are saying, so what it means is that my capacitor voltage in the solution, there would be two values of s for which we'll get the solution, and there would be two time constants, and the capacitor voltage would be a sum of those two. And so s can be, it's a quadratic equation, we can write it as minus r by 2l plus minus, and so on and so forth. So these are simple things. And you know, so instead of writing in terms of r and l, many times we write it alternatively. So this form is also useful. We can define this value as omega naught equal to 1 by root LC. And you can verify that omega naught has units of frequency or 1 over second. All right, so this is called the, later on this will make more sense in the next lecture. We may call it the resonant frequency of this particular circuit, 1 over square root LC. Right now, it's a frequency which is characteristic of the circuit that we have related to L and C here. And we can define something called Q, quality factor, as omega naught L by R. And we'll see the significance of Q in a minute. And in terms of omega naught and Q, we can write S as follows here. S by omega naught equal to minus 1 over 2Q plus minus square root 1 over 4Q square minus 1 here. So in this general form, we know that if this particular circuit will be characterized by two exponentials, and the exponentials, the time constants of the exponentials are determined by this equation here. So let's look at the behavior of this circuit in a little bit more detail here. So we have all these terms that are there here. So note that I've written now two exponentials, a e to the power s1t, s1 let's say is with the plus sign, and a e to the power s2t, s22 is with the minus sign here. So these are the two solutions that come as a natural response to the circuit when this is 0 here. And the first one is due to the forced response. So note that if I put Vc equal to Vs, Vc equal to Vs here, and then Vc equal to Vs here, then this is 0 here. So that's also a solution here. So Vct equal to Vs here and A here. So that's the net solution here of this particular circuit here, and S is given by this. Okay, so let's look at case number 1. So we have deliberately gone quickly over the maths part of it. If you have a little bit doubts here and there, you can go and read a little bit more about second order differential equations and how their solution is obtained. So let's look at case number 1. The case number 1 is where Q is less than 0.5. So note that if Q is less than 0.5, then this term, this 1 over 4Q square is greater than 1. Is greater than 1, and therefore my square root is a real quantity here. And if it's a real quantity and Q is anyway a real quantity, so the whole thing is the value of S is a real value, and you know, is negative. That is there. There's a negative term, and you can see here that this term would be is less than this particular one. So S is in general negative. So it's real and negative. The roots are real and negative. Okay. So let me take an example and show what are the consequences of this. So we are looking at Q less than 0.5. Okay. So let's take a circuit like this. We have a 10 volt supply. R1 is 1000 ohms. This is 50 millihenries, and capacitor is 1 microfarad here. And we can calculate. We know that Q is omega naught L by R. So to calculate Q, before that we have to calculate omega naught, 1 over square root LC. So omega naught we can calculate. We are given L and C. So this is the natural frequency of the circuit, 4.4 into 10 power 3 here. Frequency in there, omega naught. And Q then we can calculate comes out to be 0.224 here. So Q is less than 0.5. And then what is the behavior of the circuit? So let's look at the capacitance voltage here, right? So that's what we are interested in. So if I look at a capacitance voltage, the capacitance voltage we find, well, starts from 0, which is understood. Before the switch is closed, the capacitance is uncharged, so starts from 0. And we know that once you close the switch for a long enough time, then in steady state, capacitor will not allow any current to flow. It's an open circuit. So the net voltage across the capacitor would be 10 volt. So that's what we find. The capacitor is charging and eventually charges towards 10 volt here. So nothing, it seems to be natural. Seems to be what we expect. The capacitance should charge. And although it's not a simple exponential, single exponential, we know that there are two exponentials here with a value of S1 and an S2 here. And so Vs denotes the final part here, right? So Vs is where when all the exponentials die out, these are all negative. When all the exponentials die out, you are left with Vs, which is the supply voltage here, 10 volt here, right? Anyway, so it doesn't seem to be seems to be according to expectations. S1 by omega naught is 0.423 and S2 by omega naught. We can, for these values, we can calculate what is S1 and S2. Okay. All right. So how do we find, if you're wondering, well, how do we find the full solution? So note that from the values given in the circuit, we have been able to find Q and omega naught, and we'll be able to find S1 and S2, the two time constants that are there here. And we know Vs already. The things that are remaining are A and B. So how do we find A and B? Well, we can take the case of capacitor voltage at time t equal to 0. And we know at time t equal to 0, the capacitor will be uncharged. So that's equal to 0 here. So we get this equation. We put t equal to 0 here. So we'll get Vs plus A plus B must be equal to 0. So that's one equation. The other one that we know is that the current flowing through the capacitor will also be 0 at time t equal to 0. Why? Because initially the current through the inductor is 0, and the inductor will not allow any instantaneous change in current. So if we take the derivative of this one, the current through the inductor and current through the capacitor are obviously same. So if we take the derivative, the current will be C dV by dt here. So that's the current flowing there. And this current at time t equal to 0 must be 0 here. IC0 must be equal to 0 here. Okay, so we get this equation here. Right, so this current is 0 here, so C obviously is non-zero. So we get another equation which is Vs plus AS1 plus BS2 equal to 0. And you have another equation which is Vs plus A plus B equal to 0. So you have two equations, two unknowns, you can figure out A and B. Right, so that's the general procedure for finding out what is A and what is B. We can do that through the initial conditions. What is the initial value of the capacitor voltage? What is the initial current through the circuit? And use that to calculate the variables here, A and B. All right, so we'll not get more into this, but that's the procedure here. So for our circuit, this is what happens here. If I take my circuit and I apply all these things that we just learned, Q value is less than 0.5, and so this is what we obtain, 10 plus 0.59. So we have two time constants, as I said. One is a smaller time constant, the other one is a larger time constant here. And this is what we said is VC here. The capacitor voltage changes like this here. Capacitor charges towards the final value of 10 volts gradually with these two time constants involved. But note that this time constant is short, so capacitor is predominantly being described by this one here. This is a larger magnitude, also 10.59 here. If we look at the current, the inductor current or the current flowing through the capacitor here, the inductor current goes like this here. Note that initially the inductor current through the inductor is 0, and because the current through the inductor cannot change here, so the inductor current starts building up. Now, why does the inductor current start increasing? Well, if you think about it, inductor current starts increasing because initially I equal to 0. Right, I equal to 0, so there's no drop here, there's no drop here, and there's no drop here, and so VR equal to 0, and there's no charge on the capacitor, so VC also equal to 0. So there's nothing but KVL, source voltage equal to drop across resistor, drop across inductor, and drop across capacitor. So initially VR is 0, VC is 0, and we are left with only VL, and VL must be equal to 10. And VL equal to L di by dt. So 10 equal to L di by dt. So this di by dt is positive, and therefore the current starts building up. But then as the current starts building up, as the current starts building up, note that what happens as the current starts building up and current becomes non-zero or positive, a drop across R1, and the capacitor also starts get charged here. So what happens is the voltage across the inductor drops here. VL drops here. VL becomes smaller. And as VL becomes smaller, the rate of change of inductor current with time also becomes smaller. Eventually what happens is the current has built up to an extent where this drop and the voltage across the capacitor are such that the voltage across the inductor falls to 0. So that's where we are at the peak value. Di by dt equal to 0 here. Right, so that's how this part sort of builds up, and then after that the current keeps on charging the capacitor here. So the capacitor has to finally, remember, has to reach its value of 10. So this voltage rises further. The drop across this also rises. So this becomes negative. And as this becomes negative, VL equal to will become negative and the current starts falling here. Right, so that's the general why the current is increasing, reaching a peak value, and why is it falling. It goes because of, you can explain it on the basis of these three equations here. VL equal to L di by dt, and the Kirchhoff's voltage law, Vs equal to VR plus VL plus VC here. Okay, so the dominant, the initial current rises because of this is characterized by this time constant. And then this particular part here is described by the other time constant here. So we said there are two exponentials that are there here. So more clearly visible in IL than in this particular case here. So we've been discussing Q less than 0.5, for which the roots of this quadratic equation are all real and negative. And we call this case as an overdamped case. Overdamped case where capacitor voltage goes to its final value slowly and it monotonically increases and reaches its final value like this here. Now Q equal to 0.5 is what we call as critically damped case. So it also looks similar, right? It looks similar to this kind of a charging. Q greater than 0.5 is an interesting case. So this is overdamped. This is critically damped case, and Q greater than 0.5 is what we call as underdamped case here. So let's look at Q greater than 0.5. So now how are we altering Q? Well, a very simple way of altering Q, Q is equal to omega L by R. Omega naught L by R, and omega naught depends on L and C. So suppose I don't touch L and C, so omega naught remains the same, and I can simply change the value of R and change Q. Okay, so very easy way to change Q is, now if I make R1 let's say 10 times smaller, so Q for this circuit was 0.2. Let's see how much Q for this circuit was 0.224, I think. Okay, so if I make R1 10 times smaller, so Q is going to become 2 point something and well above our 0.5 limit here. Okay, so let's look at that underdamped case here. So Q, note that Q is 2.23. We have made the resistor smaller. And now note, if I look at this equation here, when Q is larger here, this term becomes less than 1. And so square root becomes an imaginary quantity. So we write our roots in this form here. Roots as S equal to minus omega naught by 2Q plus minus, we take the J part out, imaginary part here, 1 minus 1 over 4Q squared. So we have now roots which have a real component, negative component, and an imaginary component. So it's a complex root here, and have both real and imaginary components here. And for the circuit like this, we can show, for example, the values are all given, so we can calculate omega naught, Q, and everything. So we can see S1 is minus 1, 10 to the power 3, and this value, and S2 is also here. So the real part is the same, imaginary part is minus here and plus here. So we have two roots. And using the procedure that we talked about, we can show that when you have complex roots, well, you can write it in terms of e to the power s1t and e to the power s2t, but you can take the real and imaginary parts out and you can rewrite, we'll not go into the maths of it here, you can write the final voltage in this form here. VCT equal to 10, the final value of the capacitor voltage, and then this is what comes out of the two exponentials, e to the power s1t and e to the power s2t here. So 10 cos omega 1t and sine omega 1. So you get a sinusoids here in the solution. And omega 1 is 4.368 times 10 to the power 3 is fairly close to the omega naught that you see here. So in the cosine and the sine, there's a frequency part here, which is very close to omega naught here. So if we were to plot it out, this is how it would look. VCT equal to 10 e to the power, and there's a cosine and a sine. So cosine and sine denote oscillations. So this is what you find here. Capacitor voltage is not going monotonically to its final value of 10 volts, but it rises and sort of, overshoots, goes beyond its steady state value to something like maybe 15 volts or so, then comes back here around 7 point something, then goes here, and then these oscillations gradually die down, and which we can see this cos and sine are describing the oscillations, but the oscillations are dying down because of this negative exponential here, e to the power minus 10 to the power 3t here. So the amplitude of each one of these cosines and sines is decreasing. So there is a cosine there's a sine part here, sinusoidal part here. You can obviously combine both of them into one single cosine with some phase value here. So the amplitude is decreasing exponentially using through this particular value here. Okay, so there's an interesting behavior here. There is a capacitor voltage does not go monotonically to its final value here. In an underdamped case, there's an overshoot, there's an undershoot, and then goes, these oscillations die down and then it reaches here. So a little bit on why is this happening. Of course, it's coming from the equation. So that's mathematically, there is no problem. But in terms of physically, what is the reason? Why is this? Why does it go beyond 10 volts? Even though there is a value of 10 volts in my circuit given by power supply, the capacitor voltage is going beyond 10 volts, is going up to maybe 15 volts here. And why does it not just go towards 10 volt and saturate there as was happening in the underdamped case? Why is it going like this here? And so let's look at it in a little bit more detail here. Okay, so in this circuit, what I've done is I've plotted for this case the capacitor voltage, the inductor current in green is the inductor current here, current through the inductor or current through the capacitor, they are the same here, right? So all of them are given. So let's go step by step. Okay, so let's start with time t equal to 0. So we have just closed the switch, and when we have closed the switch, note that in green you will have the inductor current, okay, and in red you have the voltage across the capacitor. Okay, and these are the equations through which you can understand what is going on. First is the Kirchhoff's voltage law. The voltage here is equal to sum of VR plus VL plus VC. The voltage across the inductor is is related to di by dt, and the current here is I equal to C dV by dt. Anyway, so these three equations are with which you can qualitatively explain why the behavior is in this particular way, in this form here. So at time t equal to 0, right, just when we have closed the switch. Now we said before you close the switch, the charge on the capacitor is 0, there is no current flowing here. So obviously the current, because of the inductor would not allow an instantaneous change in current. So the current remains 0. The current remains 0. Note that the scales, the green one is the scale here. So current remains 0. And the capacitor voltage also remains 0 here. So that's what we have indicated, 0, 0 here. But KVL has to be satisfied. So where does this 10 volt go? The 10 volt is all across the inductor. Now, if 10 volt is across the inductor, so VL is 10. And 10 equal to L di by dt. So what will happen? It denotes a large change in the current with respect to time. Di by dt is large. So that's why the inductor the current across the inductor starts to increase. Now, as the current through the inductor starts to increase, note that what will happen. As the current through the inductor becomes positive and starts to increase, there will be more drop across R1. And the current will charge up the capacitor, so the voltage across the capacitor will increase. So both, if I look at this equation, VR will increase and VC will increase, but VS is constant, so VL has to decrease. And if VL has to decrease, if VL decreases and di by dt decreases here. So the current then starts off very sharply, but then the curve starts bending because di by dt has to reduce. So let's look at another scenario here. Okay, so we are here. at this particular point. The capacitor has charged somewhat. The inductor current has risen to some value here. And note the value here. There is a drop across the resistor now. There's a drop across the capacitor now. And the drop across the inductor is less now because 10 must be, KVL must be satisfied. So it's 4.2. And because it's 4.2, the current is now no longer increasing as sharply as it was at time t equal to 0. So the curve is bending. Now you may imagine if this continues, the current keeps on building, this drop will increase, this drop will increase. Eventually what will happen is the drop here will fall to 0. And when the drop here fall to 0, VL will fall to 0. It means di by dt is 0, which means we have reached the peak of the inductor current here. We've reached here. So let's look at this situation here. So note we are at this particular stage here. The current through the inductor has reached its peak value. So voltage is 0. The capacitor by that time has charged to 6.6 volt here. It's not fully charged. 6.6 volt. And the voltage drop across R1 is 3.4 here. So the current through the inductor keeps on flowing. Note that the current is still flowing. The current is how much? Current is around 30 milliamperes or so. So this current is flowing. So the capacitor would charge. And as the capacitor charges, this voltage will rise. And then to satisfy this 10 here, the drop here will become negative. Okay, so that's what would happen. Let's say if I go down here, why the current, note that if the current reaches a peak, you can easily think that it cannot remain constant. Because if the current reaches a peak and if it were to remain constant, that this voltage rises, and this drop increases, and if it reaches a peak and remains constant, this is 0 here, so that's incompatible with KVL here, right? So current has to, after reaching a peak, the current has to decrease. The current has to decrease. The moment the current decreases, note that according to di by dt becomes less than 0, the voltage across the capacitor becomes negative. So look what happens when we are here. Next case. When we are here, so we still have current here. So current is positive. So there's a drop here, 2.63 volt here. And now note that the voltage across the inductor has become negative, right? Because di by dt is negative. So this is minus 3.9. So now to maintain, because the voltage across the inductor has become negative, to maintain the KVL here, this voltage is 11.27. Right? So that's from the KVL. So you can see here it has become larger than 10. Why has it become larger than 10? Because we have the inductor voltage which is negative. And which is negative. So KVL is requiring it to become a larger than 10 value here. So if this is negative and if the drop here is larger than this value here, right? So why is it larger? Because R is small. We have chosen R is equal to 100 ohms. So the drop here is not that large. So this becomes, the drop here becomes significant and becomes larger than this. Okay, negative and larger. If we had chosen R larger, then the drop across R would have been larger and maybe this would not have happened. Okay, but in this case, so the total drop across RL part is negative, and therefore to maintain the KVL 10, this has to increase here. Okay, so it's a question of what is the value of R and what is the value of L. We have to look at it, and under these conditions, under damped case, so this is what is happening. And this has gone to 11.27 at this particular point here. But note that the current is flowing. The current is positive. So this current here will keep on charging C. So it will rise even beyond 11.27. And it will keep on charging till the current here is positive. So it will keep on charging till the inductor current falls to 0. So let's look at this condition here. Once the inductor current falls to 0, the capacitor voltage will reach its maximum value. And then we will see that the inductor current has to become negative. Okay, so let's look at, now you may be wondering, why does this happen only in the underdamped case here? What about overdamped case? You may be thinking, well, in the overdamped case also I have an inductor, I have an R and I have a C. So these things should be happening even there. But the difference was there in the overdamped case, we had a larger value of R. We had a larger value of R and things are different. So let me go back to an overdamped case with a larger value 1000 ohms here instead of 100. So note at this particular point when the inductor current is decreasing. So the capacitor voltage is 2.5. Note because of a larger value this is 7.9 and the drop across the inductor is much smaller. the drop across the inductor is much smaller. So together the RL part, the drop is positive, right? If the drop is positive here, and then this adds up to give rise to a 10. So there is no overshoot in this particular case here, because there is a negative voltage here across the inductor, but it's much smaller. There's a lot more voltage across the resistor here. Okay, so that phenomena doesn't happen in this case here. So let's continue with that. So we are here at this particular point. Inductor current is decreasing. Because of that, there is a negative value across the inductor voltage here. The drop across the resistor is not that large here because of the small value of the resistor here. And then the capacitor has gone beyond the value of 10 volt here. Okay, so the current which is large in the circuit has charged up the capacitor to a value which is larger here. So, and capacitor keeps on charging. So let's go here to this point here, where the inductor current falls to 0. So inductor current falls to 0, the drop across the resistor is 0 here, and the capacitor is charged to 14.82. And to maintain KVL, we can see here there is minus 4.82 here. So now that there is minus 4.82 note here, this is negative here. So which means di by dt is negative. So the current will keep on decreasing. The current will not go to 0 here and stop here. That cannot happen. So the current will keep on decreasing here. As the current becomes negative, now the capacitor starts discharging, right? So this is what happens here. Note that the capacitor starts discharging. So from a value of 14.82, it discharges here to 11.56. And because we have reached the peak of the inductor current in the negative direction, the drop here is 0, and the drop here is minus 1.56. But then note that the inductor current is still negative, so the capacitor voltage will keep on decreasing. And the capacitor does not, again, just like there was an overshoot here, the capacitor will not settle down at 10, but there's an undershoot here. So look at what happens here at this point here. When the inductor current falls to 0, the capacitor then falls to 7.67 volts here. So again, this is not sustainable. The current is 0. But for the final value, this should have been 10 volt. So now and this should have been 0. But now there is a voltage across the inductor 2.33 here. So that will cause the inductor current to rise again. It rises again here. But note, this point is different from this point. At this point, the voltage across the inductor was 10. So it rose much higher here. At this point, the voltage across the inductor is only 2.33. And the capacitor has already charged to 7.67. So it rises. It again happens, the same thing happens, but on a smaller scale. And so this repeats, and it happens on an even smaller scale, and eventually these oscillations, they die down. And we get the steady state value here. Right, so at this point, this is what you get here. So 11.1 minus 1.1, and eventually, as I said, it dies down here. So this is the expression here, e to the power minus 10 to the power 3t here. So the rate at which the oscillations are dying down depends on this 10 to the power 3t here. And this real part, negative part, is this omega naught by 2q here. This is this part here. And so if we make q even higher, let's say right now we have a q of something like 2.2. If we make q even higher by, let's say, reducing the value of r, q is what? Omega naught L by r. So if we reduce the value of r even further, so q will become even higher, and this will become smaller. And this part becomes smaller, which means this 10 to the power 3 part becomes smaller. And as this becomes smaller, then the oscillations will die out slowly. Okay, so q is omega naught L by r. And this term that you see here is r by 2lt here. If we put in the values here, r by 2l into t here. And we, as I said, if we make the q larger by making r smaller, then this part becomes smaller and the oscillations die out slowly here. So let's look at that. We made from 100 ohms to 25 ohms. Q becomes 8.92 here. And look at the oscillations in the capacitor voltage here. Capacitor voltage goes even higher. Earlier it was going to some 14.8. Now maybe it's going to us 18 or something. And then it slowly dies down here. Right? So that's what happens here. So these oscillations in an underdamped case, if Q happens to be greater than 0.5, these oscillations begin to appear in the system here, in my LCR circuit here. And this is not just in the charging case, I could do the same thing in discharge case. So initially assume that the switch is closed. If the switch is closed and closed for a long time, then what will happen is the current will be 0, but the capacitor would be charged to 10 volt here. But now you open the switch here, and now the circuit has and there's a resistor also here. So the capacitor will discharge. And in the overdamped case, note that the capacitor discharges finally to 0, just like looks like a simple RC circuit here. But if because the Q of the circuit is less than 0.5. But if I have an underdamped case with smaller values of resistors here, look at again the capacitor, the red one, the capacitor discharges, it starts from 10 volt, and then instead of going to 0, goes to -5, and then goes to maybe 2.5, and then goes here, and then gradually settles down to a 0 value here. So there's again these oscillations that manifest itself when the resistors are smaller and Q factor is greater than 1. Mathematically, because we get complex roots, and the complex numbers denote the sine and cosine kind of a behavior here. Okay. So just what we talked about series RLC circuit, similar things happen in parallel RL circuit. So in parallel RL circuit, we can mathematically, again, we can go ahead and show, for example, Vs will be equal to I is the current flowing here in this resistor, I times R plus VL. The current here will divide between the two currents here. So I equal to C dV by dt, the current flowing through the capacitor, and then the current flowing through inductor. So in this case, in the parallel, what we'll do is we'll try to get an equation for current flowing through the inductor as a function of time. So VL equal to L di by dt here. So we combine these equations and we will get this second order differential equation, which also we can write in this form, similar form like for the series RLC circuit, but note we are writing in terms of IL, the current here. And also this also we can write it as same thing. We can try a solution of the form e to the power st. We'll get this quadratic equation, and similarly the roots of the quadratic equation will be here. And same definition, omega naught is 1 over root LC. But this is where the difference is. Q we define as R by omega naught L. Instead of omega naught L by R, this is a different circuit, parallel RLC circuit, R by omega naught L. And then the equation is of the same form, S by omega naught minus 1 over 2 key plus minus and all that. Except that Q is R by omega naught L. Omega naught remains as 1 over square root LC. And the form of the current IL remains the same, just like the capacitor voltage. Okay. Note that this one looks like it's not a completely parallel circuit, but we can use source transformation Vs and R. Once you close the switch, Vs and R, we can close the switch and write it like this here, right? Vs by R, R, L, and C. So it becomes a completely parallel circuit. And the previous one was a complete series circuit, and this is a completely parallel circuit here. And the two are complementary in the sense that, capacitance voltage here, whatever we studied was happening to capacitor voltage, something similar is happening to the inductor current here. So this is how the inductor current would look like. This is the equation, the inductor current. The final value we understand. The final value would be under steady state, the capacitor is open, the inductor will be a short, so the current would be Vs by R here. And then these are the natural response of the circuit, and it has two exponentials, S1 and S2 here. And we've seen these values, S and all that, calculated using these expressions. And Q is R by omega naught L. So again, we have two cases, underdamped, Q less than 0.5. So we are looking at IL. How does IL go from its initial value of 0 to its final value of Vs by R? Okay. So Q is overdamped. So we've chosen a value of smaller to keep Q small. We choose a small value of R, 100 ohms here. And we keep L and C just like in the previous case here. And note that the inductor current starts from 0. In green is the inductor current, starts from 0 and reaches its final value. Right, reaches its final value, which is equal to basically 10 divided by 100 ohms, 100 milliamperes here. So green shows the 100 milliamperes. So this was the behavior of capacitance voltage in the series resonance, series RLC circuit. This is the behavior of inductor in parallel RLC circuit here, right? And the capacitance behaves in a manner similar to what the inductor current was behaving. Q is 0.447 here. Now let's make R1 larger, let's say 10 times higher. If I make it 10 times higher, it will become 4.4, and then we go into a underdamped case here. So underdamped Q equal to 4.47. So now again the inductor current starts from 0, but doesn't reach its final value of 10 milliamperes straight away. It overshoots, and then there's an undershoot here and overshoot here, gradually smaller and smaller, and then it settles down here. So that's the characteristics of a underdamped case here, right? So we'll not go into the details. Similar things are happening here. Inductors charging, capacitors discharging, similar things that we discussed in series RLC circuit here. Except that note that Q is R by omega naught L in this case here. Now oscillators, note that what is an oscillator? Well, many times we require a sinusoidal oscillator for various purposes, and we have to generate a sinusoid. So we are seeing how a sinusoid is generated here. So we simply close the switch here. If we let's say at time t equal to 0, if we close the switch, we are seeing that we are exciting oscillations in the circuit. If you look at, let's say, the capacitor voltage here, or the output voltage here, let's say, the capacitor voltage is going like this here, right? A sinusoid. And the frequency is defined by L and C, omega naught equal to 1 over square root L and C. So we are creating a sinusoid, but what is happening is the sinusoid is actually decaying. After a while, it becomes 0. Now in an oscillator, we would like the sinusoid to continue. You know, it reaches a positive state, then reaches here, and then it should go back to the same state here. And the reason why is decreasing is because of this presence of R here. Note that if I make this R even larger, right? So the oscillations will die down even slower. So basically what we need is, in an oscillator, we need to cancel the effects of R. So the oscillator circuit uses a amplifier along with a L and a C, and to cancel the effects of R and make oscillations which are sustained, which will continue to have a constant amplitude and not a decaying amplitude because of the resistor values here. Okay, so let's so these RLC series and parallel circuits are very, very important. In fact, antennas which are necessary for communication, for example, antennas can all be thought of as a let's say a parallel or a series resonance, parallel or a series circuit here, or some combinations of that. So these in their equivalent form, they are essential components of all antennas that are there here, these LCR circuits. All right, so let's stop here.